All of the problems recorded in my videos can be downloaded at statisticsworkbook.com. If you go to the website, click on the PDF, and you can download a copy of the entire workbook for yourself. Also on the website, you'll find access to all of my videos that I've produced on statistics, not only the ones uploaded to YouTube. I've uploaded over 100 videos that just aren't available on YouTube. So, I hope you'll check out statisticsworkbook.com. Alright, let's begin. Hello and welcome back. This next exercise now we're going to look at another single factor ANOVA. This time we're going to consider what is called a randomized block design. So we've talked about, in Module 10, we talked about different sources of variation within a data set. In that chapter, or that module, when we were looking at the difference between a two-independent random sample design and a matched sample design. You may recall that in that case we had two different sources of variation that we discussed. One was due to differences between the individual treatments, or differences between the two samples, and another source of variation arose due to the fact that there were innate differences between our observational units, or between the entities that we were observing, that we were obtaining the data from. So by developing an experiment as a matched sample design, we are able to remove one source of variation from that data set. Well, the randomized block design is the multi-population analog to the matched sample design. So again, what we're going to be doing here is controlling for another source of variation in the data set. So the fundamental process is going to be very much the same. We are still going to be doing what we call partitioning the variation within the data set. So we still have sum of squares total, which represents the total magnitude of variation within the data set. We still have sum of squares treatment, which represents the magnitude of the variation in the data set due to differences across treatments. And that is still what we're testing for. We're still testing to see is there difference across our treatments. But in doing so, we account for this additional source of variation called sum of squares due to blocks. So what we call blocks is what we used to call our experimental units or our observational units. Now we call them our blocks. So we account for that additional source of variation that differences across our observational units introduce to the data set. And then we have still SSE, which is just random variation that exists in the data. So the formulas that we're going to use will all look similar. SST, this one is still just the differences between individual observations and the grand mean squared, and we add all of those up across I equals 1 through B. We say B for blocks instead of N for observations. So we add those up across all of our blocks, and we add those up across all of our treatments. So a very similar calculation, although the notation has changed just ever so slightly. We then have SSTR, our sum of squares due to blocks, and this calculation is very much the same. It's the difference between our our treatment means and the grand mean. And in the completely randomized design, we had in here this NJ, where we were multiplying through by the number of observations in that relevant treatment mean. Well, now because of how this experiment is designed, we will always have samples with the same number of observations. So we take that N out. When I say out, I say we take it out of that summation and we put it on the outside, and now we call it B because we're talking about blocks, not just the sample size N. But still, it's basically the same calculation. It's just the notation changes and sometimes throws students off. Next, SSBL. This one too, it's a very similar calculation. We're looking at now block means and the difference between block means and the grand mean. You see on our data set here, which we'll get to in a second, we've got block means as well as treatment means. And same thing, we add all of those up across our blocks and we multiply it here by K, which is the number of observations in that block mean. So if I just pick this block mean here, Well, that's the average of these k equals 3 different treatments, different observations within that treatment. Different number of observations within that block. So we have sum of squares total, treatment, block. Now, for SSE, this went from being one of the easier calculations in the completely randomized design to now being one where it starts to actually exceed the math prerequisites of a typical statistics course at this level. It would require matrix algebra to calculate sum of squares error. So what we do is we take advantage of this relationship. So we can calculate SSE by SST minus SSTR minus SSBL, and then we can obtain SSE. So we can calculate each of these three components, and then we can figure out what SSE is. Now, for the benefit of my students, SST is a long, tedious, time-consuming calculation. Just in an exercise like this, I have 15 observations, so that's 15 differences squared and added together. So normally what I do is I give students SST or I give students SSE, and then they can fill in whichever is missing. You can see in this exercise here, I've got SST is given just right here. Okay, so enough about that. Let's get into our exercise and we'll crunch some numbers. Okay, so here we have Everything Co. frequently relies on courier services to deliver sensitive documents between its regional offices. There are 3 courier companies available. Each one offers loyalty discounts, giving the incentive for customers to choose one courier and stick with it. You decide to perform a test to determine if there is a difference in delivery times between the 3 courier options you have. You send 3 packages of equal size to each of the 5 regional offices. Each package is sent through one of the 3 couriers. Okay, so what we're studying here, so our factor of investigation, we're studying delivery services. We have 3 treatments, option A, option B, option 3. We have three treatments that we're considering. Our blocks in this case, well, here I have 5 blocks. So let me write some notation here. K is 3 treatments. B is 5 blocks. So what are these blocks? Why do we separate these, or why do we need to account for this additional source of variation? Well, let me just scroll down just a little bit here. Imagine this scenario. Let's say this is our headquarters, and here we want to evaluate delivery time between these 3 couriers. So that's my main variable of investigation. But the regional offices are probably not all equal distant from the headquarters. I might have one regional office here, another one is up here, another one maybe is way down here, another one is right here. And so we've got various distances, we've got these innate differences, this heterogeneity between my regional offices. So I send 3 packages to this one. I send 3 packages to this one. I send 3 packages out to this one, and same for this one here. So when we're considering our data, there's going to be, again, random variation in that data, sum of squares error. There's going to be variation in that data set. Oh, these errors are wrong. Those ones are coming from HQ. There's going to be random variation in this data set stemming from differences between the courier services. There'll also be variation introduced into this data set due to differences in our observational units, which in this case, those differences are the different distances from headquarters. So that innate difference across our observational units, that introduces this other source of variation that we are going to account for in our calculations. If we account for that source of variation, it makes it easier to then identify a difference that can be attributed to differences across treatments. Okay, so let's get into the calculations here, and then we'll see what we come up with. So here's SST we've got. Let's fill in our table down here. So this is going to be treatments. This will be blocks, error, and total. sum of squares, degrees of freedom, mean square, F statistic, p-value, and critical F. Our sum of squares total was given to us, what was it, 15, 11, 52. 15, 11, 52. Okay, I'm just copying that straight from right here. So let's go ahead and calculate now. Well, let's set up our hypotheses first, our null and our alternative. So again, we are just testing for equality across our means. So we have mu A, mu B, mu C. Not all are equal. And let's perform this at the 0.5 level of significance. Now let's go ahead and calculate all of our different sources of variation. So SSTR. So here I'm going to be using this formula here. So first I need number of blocks. I have 5 blocks. And now we need, oh, we forgot one piece. Forgot one ingredient. I need a grand mean for most of these calculations. So the grand mean from the completely randomized experiments, you'll maybe remember I talked a little bit about being cautious calculating that and calculating a weighted average of your sample means. And only in the case when your samples had the same number of observations could you rely on using a mean of the means. Well, in a randomized block design, your samples will always have the same number of observations in them. So here we can rely on taking the mean of the means in order to obtain our grand mean. And it makes no difference if you calculate the mean of the treatment means or the mean of the block means. You should definitely always get the same result. So I'll use treatment means because there's usually fewer treatments than there are blocks. And so it's a little bit of a shorter calculation. 31.4 plus 28.3 plus 30.5 divided by 3. Let's just round that to 30.1. So there's 30.1 as my grand mean. Okay, so now we can go ahead with the rest of our calculation. So I'm going to be looking at these 3 treatment means. 31.4 minus the grand mean, 30.1 squared. Plus the next one, 28.3 minus 30.1 squared, plus the next, the last 30.5 minus 30.1 squared. And so we'll calculate those differences, square them, add them together, and multiply through by 5. So let's find my calculator, and somewhere convenient, maybe right here is okay. Will that work? Sure. Okay, you can fast forward this part of the video if I'm doing these calculations, because I'm going to do them slowly because I'm nervous about making silly mistakes and having to re-record or edit this video. So I'm going to go through it slowly. You can fast forward. I'm going to open brackets, 30.4 minus 30.1, close brackets, squared. Where's my square? Oh, did I lose my square? There we go. Squared. Plus, open brackets, 28.3 minus 30.1, 30.5 minus 30.1 equals 5.09, and times that by 5, 25.45. Okay, good. 25? 24. 25.45. 25.45. Degrees of freedom on treatments, k minus 1. We had 3 treatments, so k minus 1 is 2. And mean squared is then our SSTR, which is already in the calculator, 25.45, divided by 2 degrees of freedom, so 12.73. Okay. That's it. Now we can do the blocks. Now this one's going to be a little bit longer of a calculation because instead of just 3 means, I have 5 block means. So instead of 3 squared differences, we're going to have 5 squared differences. So let me clean up some space here. We're going to be using this formula here. It might be a little bit crowded in this space. SSBL equals, so K, this K here, number of treatments, I have 3. And now I need to squeeze in. I'm going to start off here. 26.8 minus, always working with that grand mean. 30.1 squared plus the next one here. 47.6. Next one is 21.5. Next is 33.7. Is that going to fit? And last one, 20.8. Just fits. Okay, let's get that calculator. This one might take a little while. Fast forward again if you want. I don't blame you. Okay, 26.8. $47.6. Plus 21, so next one's 33.7 minus 30.1 squared plus the last one, 20.8 minus 30.1 squared equals 490.55, and then we have to times that by 3 equals 1471.65. Okay, now we're getting somewhere. 1471.65. Good. Degrees of freedom on blocks. This is B minus 1. So we had 5 blocks. 5 minus 1 is 4. And so mean square block is 1471.65 divided by 4. 367.91. 367.91. Okay. Now, sum of squared error. So again, we've already got sum of squares treatment, blocks, and sum of squares total was given to us. So I can just calculate from SST 15, 11, 52 minus sum of squares block 1471.65 minus sum of squares treatment 25.45 equals 1442. 1442. Degrees of freedom on error. This one's a little bit different. This one is K minus 1 times B minus 1. So this is the product of the two that are right above it. 2 times 4. So this is 8. Degrees of freedom total. This is NT minus 1. Total number of observations minus 1. So 15 minus 1 is 14. What you can also see is 8 plus 4 plus 2 is 14. Okay, almost done. We need MSE. So that's our 1442 divided by 8 degrees of freedom, 1.8. So I have 1.8 is my mean squared error. Finally, now we can obtain our F statistic, which is MSTR over MSE. We don't need actually MSBL at this point. We're not going to use MSBL, all MSBL, the mean squared block. All we're doing is accounting for that variation that exists due to blocking. So now it's been taken out of the equation. Now we can calculate just our F statistics with a ratio of MSTR. Oops, let's move this out of here. So 12.73 divided by 1.8 is let's call it 7.1. 7.1. Okay, now let's get our critical value. So we're doing this test at the 0.5 level of significance. We have 2 degrees of freedom in the numerator, right? That's our 2 degrees of freedom here. And our denominator, well, that's degrees of freedom for MSE. So that's 8 degrees of freedom in the denominator. So if we go to our F tables, oh, we've already got some scribbles on here. So we have 2 degrees of freedom. Let me grab a highlighter, it'll be easier. 2 degrees of freedom numerator, 8 degrees of freedom denominator. And here we have our alpha is 0.05. And so that corresponds here. I'm looking down from here and across. So that gives me a critical value of 4.459. So here we are, here we are, 4.459 is our critical value. So we have an F distribution, looks something like this, 4.459. We reject for a test statistic larger than 4.459. Here we have a test statistic somewhere up here at 7.1. So it feels like we are going to be able to reject based on that critical value approach. Let's find our p-value just for completeness. So here we have again 2 and 8 degrees of freedom. Our test statistic was 7.1. So right kind of somewhere in between these two values, which means our p-value is going to be somewhere in between those two. So something less than 0.25 and greater than 0.1. So p is less than 0.025 and greater than 0.1. So based on those results, again, our p-value is less than alpha. Our alpha was 0.05. Our critical value approach, our test statistic is much larger than our critical value approach. So here we can comfortably reject this null hypothesis. We do have evidence to show that there is a difference between these 3 courier services. Okay, so that's it. We've got it set. We've answered our question. We've gone through some tedious calculations. This video has come out a little bit longer than I wanted it to be, but a new topic, so it takes a little bit of time. Okay, so I hope that was helpful. I think we're going to do probably at least one more here. So, okay, thank you very much for watching. Bye-bye.